zip the 3 files we added. But then, like in the other homework, it says like the whole project. What do you want?
Let's zip the whole project.
Whole project. Cool. Thanks.
Yeah, they have any. My buddy said I'm in here. He was very good. Let's see. He says, I don't think I did anything special. Did you put the camera far away, or maybe there's too much of an echo in the flash?
I don't think the problem was about it picking up extra sound. I think it just being like
Interference.
Alright, let's get started.
turn off the light.
The second from the right on the one that's open. Yeah.
Okay, let's get started. Can you guys hear me in the back? Good? Awesome. Okay, so today we're going to finish up informed search. And I decided to also do kind of a review of search. So we'll do some problems on the chalkboard. And then we'll save the next lecture for next week. Some announcements and questions to you all. Who's done the project in Python 3? Okay. Who had issues with the autograder? Okay, so we're working out some issue with the autograder. We'll figure that out. Were you also working in Windows? Yeah. Was anybody else working in Windows and it worked for them? Okay, so it'll work somehow. We'll figure it out. Because of these issues and some other things, I think I'm going to extend the due date of the project to give us time to work on this and make sure we can sort through that. And then I'll probably extend it. Is that okay with you all? Sure. Okay, so we'll probably do Tuesday night instead of tomorrow night. Yes. Yeah, so for this project, you can do it in either 2 or 3. Yes?
So, after this project, are we just switching to Python 3? Or
We're still working through that. That's what we're trying to decide. If we can get Python 3 working, what we would like to do is switch to just Python 3, which some people are raising the roof about, which I think is enthusiasm. That is another good reason to extend the due date on on Project Zero. The whole point of Project Zero is to get you kind of familiar with Python if you've never seen it before, and make sure that kind of your coding environment is working with the project infrastructure. So this one can be done in 2 or 3. Tentatively, we're saying we'd like things to be done in 3, but since we have these moving forward after this project, but since we're having these problems, I'm not going to commit to that yet. If we get those sorted and it's reasonable and it's working for everybody, we'd like to switch to just 3 for consistency, because some of the projects have kind of differences between the 2 and the 3 version that makes it a little more difficult. Does that sound good? Yes?
So if we're pairing up with someone, are we just submitting one file?
Well, you should work on your own for this project, Project Zero. When we do the groups of up to 2, we're going to use the group mechanism in Canvas. And so I believe for the code, you only submit 1 version, but there's kind of these self-assessment questions. Those need to be submitted individually too. So we'll probably do the code in 1 version, PDFs for each. That sound good? Okay, cool. So we'll extend the due date of Project Zero to Tuesday at midnight instead of Friday at midnight. One more question. Does anybody want us to stop using midnight and start using a more reasonable hour like 5 p.m. to kind of force you to have nights? Okay. Okay. 4 a.m. 4 a.m. Yeah, that's the worst of all worlds. A lot of our paper deadlines are, midnight anywhere on Earth, and so we're here until 7 or 8 a.m. It's a bummer. Anyway, okay. At least that's what it was. All right. So, great. Regarding this project, if you haven't already turned it in, just zip up all the files, including the ones you modified. If you have already turned it in and you just did the 3, that's fine. I think we had it differently listed in different places, so we'll make sure that's consistent moving forward. Does that sound good? Cool. I appreciate you all being very gracious guinea pigs on the transition from 2 to 3 that we're encountering this semester. So I appreciate that. Okay. Next announcement. Quiz 1 opens at the end of class today. It is due tomorrow at midnight, well, a minute before midnight. It is longer than Quiz 0, and I'm not giving you the answers in advance. So allow more time for yourself. If you open it up and you have to do something 2 minutes later, that might be an issue. Yes?
Will there be a time limit on this quiz, or is it?
I believe there is no time limit, but I'm not sure what Canvas does if you leave it in the middle. I'm not positive. So.
I have left quizzes, and they just kind of stay.
Okay, that's good then.
Yeah.
Awesome. This is my first experience with Canvas this semester, so I'm still kind of working through the kinks myself. Okay. Good. All right. Does this all sound good to everybody then for now? Yes.
Will the quizzes be similar to Quiz 0, where it's based on most of the stuff on lecture, or?
Yes, so it's generally going to be from lecture. There may be some stuff from the reading assignments. The quizzes are designed to be kind of easier. The homeworks will be a little more involved. And you should see the first homework probably on Tuesday of next week. So that's our goal for this. Okay. But moving forward, the quizzes will be more like Quiz 1 than like Quiz 0. So to kind of give you a sense for the scope moving forward. Okay. All right, so last time we went through informed tree search. And we talked about heuristics and what makes them admissible, what makes them good. We talked about greedy search, which is where you use just the heuristic value to order your expansions. We talked about A-star search, where you're using both your backward cost and your heuristics or forward cost. Today, we're going to finally distinguish between tree search and graph search. So we've been talking about tree search up until now. We're going to change that algorithm very slightly, which I've kind of hinted at in various parts in order to be a little better in some specific ways. So that's what I'm going to talk about today, and then we'll do some review. All right, graph search. So the intuition here is that if we, during tree search, fail to detect repeated states, then we can get unnecessary work being done in the tree search. So if you look at this state graph here on the left, the search tree looks like this. And so there's repeated structure here, right? And this is in this very toy example because we have multiple edges from A to B, but this also exists, this issue exists in graphs that don't have this double edge situation. So for instance, this is the search tree from that example we used a bunch this whole last week, right? You all remember this? Okay, so what I want you to note is that these highlighted states here, what exists under them is duplicated elsewhere in the tree, and in fact is duplicated elsewhere in places we would have looked first. Do you see that point? So if you look at E specifically, this is a good example. This subtree here is going to be identical to this subtree here, that if we're doing BFS, we will have explored first, right? So it doesn't make any sense, really, to consider this part of the tree when we're getting exactly the same tree structure over here, but at a lower cost. Does that make sense? Okay, so how do we enforce this concept? So the idea in graph search is that we're never going to expand a state twice. So this is going to work almost identical to tree search, except we're going to keep around a set of states called the closed set. And when we expand a tree search node, before we then expand that node by adding its children onto the frontier, we're going to instead check to make sure that that state has never been expanded before. So if we've seen it before and expanded it before, we're just going to throw it away. Otherwise, we're going to continue as if it was tree search. Does that make sense? So this is an important implementation detail. You should store this set as a set when you're looking at what data structures to choose from in your implementation. You store it as a list in a non-trivial size search. It's going to grow and grow and grow, and depending on the complexity of searching that list, you can run into problems. Does that make sense? Cool. So I think all of the commonly used modern object-oriented languages have set data structures in their standard libraries. So you should consider that. Can graph search, this addition to tree search, wreck completeness? Who says it can? Who says it cannot? Okay, somebody who said it cannot, who wants to tell me why? Yes?
I mean, you're only basically stopping the expansion of the state if you've already visited it. So you're ensuring that you've already visited it. I could see, like, maybe if the states, and the way you were storing them in the set, was like a string title and two states have the same title, you could run into an issue. But other than that, you should be able to go through the whole tree and visit everything, and then you are just basically caching results.
So that brings up a good point. If you're not careful about how you're implementing the set, and you can have collisions that aren't truly collisions or something if you're doing like hashing or whatever, you have to be careful there and make sure that you're not throwing away states that are similar according to your set definition but not similar according to the true definition, right? But yes, the concept generally is completeness means we will find a path if one exists. We're only getting rid of duplicate work, so if we were going to find a path anyway, we'll find it without duplicating it, right? What about optimality? Who thinks this can be an issue with optimality? Who says it would not be an issue? Okay, let's look at an instance of A-star search where it goes wrong, which should tell you the answer to that question. Okay, so here's our state space graph and here are our heuristics. Okay, let's double check that this looks admissible, right? So we want to be less than or equal to the optimal path to the goal at every state, right? So S's heuristic value is 2. Nothing's less than 2, B is 1, nothing's less than 1 from B, A is 4, 4 is exactly the optimal path from A, and C is 1, and that's less than 3, and then the goal heuristic is 0. Right, this is admissible. But let's see what happens when we build up the search tree but keep around this notion of the closed set. Okay, so we start with the start state, then we expand from there, its children, right? We're going to expand the lowest cost, F cost 1 there, and that brings us with C on the frontier. We expand the lowest cost there, which is C, and we add the goal value to the frontier, right? And then we pop off the one with the lowest F cost, which is A at this point, right? Because the goal is sitting on the frontier. We haven't popped it off, which is when we would check, right? So then we add C on, right? At this point, we would expand C, right? But we already expanded C down the right side of that tree. So C exists on our closed set. So we don't. Right, we just throw it away. Yes?
Can we see to fix this by like having our closed set use C, comma, value at C as the start?
It gets a little more complicated. Yeah, that's one way to do it. Probably I'd have to think about it a little more. There are ways to get around this where you start saying what is the cost of the optimal path to this point. But I'm going to talk about a different way to approach this problem right now. So anyway, the point is we don't expand C. That means we pop off G. We have a suboptimal solution returned by A star, right? If instead we allowed this C to be expanded, we would find the optimal goal, right? And then we pop that goal off. That's the optimal solution that we wanted to have been returned by A star. So that's going to bring up an issue with this heuristic. And so this heuristic's admissible, but in this case, that might not be enough. So we're going to talk about a condition that heuristics can have called consistency. So the main idea of admissibility is that the estimated heuristic cost is less than the actual cost on the path to the goal, right? But we want to kind of expand this and make sure that this is the case all through the tree. So admissibility, the heuristic cost is less than the actual cost. That's the case with this example here, where we have this heuristic of 4. That's exactly equal to the actual cost, so it's less than or equal to the cost from A to G, right? Consistency means that if we consider the heuristic arc cost, that's going to be less than the actual cost per edge. So what this means is that if we go from A to C and that costs us 1, but our heuristic value was 4 at A and our heuristic value is 1 at C, that's inconsistent, right? That doesn't make any sense. We thought it was 4, we went 1 step in cost, and now we think it's 1. We should really think that's 2 at A, right? That's the thing that makes sense. So consistency means that the heuristic value difference across an edge is less than or equal to the cost across that edge, right? And that holds for subpaths as well, but that follows from this. Okay. Does that make sense? All right. So what are some of the consequences of consistency? That means that the f value along a path never decreases. And so if we add this condition, A star becomes optimal again, right? Okay. So A star is optimal with consistency. You can work this proof out. It's very similar in structure to the proof we did last time. I would encourage you to try it at home. But in general, most natural admissible heuristics tend to be consistent, especially if they came from some relaxed problem. Consistency implies admissibility. That's important. Consistency is a stronger condition than admissibility. Okay, cool. So in summary for A star uses both backward costs and estimates of the forward cost. And it's optimal with admissible and consistent heuristics. If you're doing tree search, it's optimal with just admissible heuristics. And the key to using A star in practice generally is to find heuristics for your problem. And relaxed problem heuristics can be a good starting point for that. Okay, so here's the tree search pseudocode. This is in your book. It is only slightly modified here where we check whether a state is not in the closed set in order to turn it into graph search. Yes?
So if you were to have graph search without a consistent heuristic, would it be possible to fix it by just, when you see something that you've already expanded, and if the backwards cost is less, you just move that whole subtree over?
Yeah, so I believe what you would want to do is replace that node with the more optimal path to that node that you found up until that point, and keep going in that way.
Keep optimality?
Yes, so there's a way to do it that way. I don't want to speak imprecisely. Let me double check the very specifics about that, and I'll bring it back on Tuesday. We can talk about it. That's fine. Okay. All right, so let's do a review of all of the search we've talked about up to this point, because it's a really important concept. So what we're going to do is we're going to go over some problems, both tree search and graph search, with the various search algorithms that we've seen. This is going to be very similar to questions that you'll find on the quizzes and on the homework. So that might be a reason to stick around. Also, if there's time, I'm going to talk about some search, how we would abstract a self-driving car navigation problem to search. And that process of constructing that abstraction and constructing the search problem from a problem like that might lend insight to questions that are on the quizzes or the homeworks. So that might also be a reason to stick around. But anyway, let's do this on the board. So let me see if I can figure out this. I'm going to try to lead this up on the right there. This is the graph we're going to work with. Okay, so let's talk about tree search over this graph here. So the first thing we could do, if we want to kind of conceptualize how this would work, is we could build up the search tree from the graph, right? So let's do that. So we have here our start node, right? And so this node has two children, A and B. Can you guys see this color? Right? Okay. A has one child, that's G. B has three children, C, D, and also G. And then each of these has one child, which is G. Right? Does this look right? Everybody? Okay, cool. So let's keep that around and let's search over it. So let's start with depth first search. So in depth first search, we're going to keep track of our frontier with what kind of data structure? Depth first search. Stack. Let's do stack. Okay. So let's just explicitly keep our stack around. Okay. So let's start this search. What goes on our stack first?
Start or start?
S. So we'll put S on, right? Then what do we do? Okay, so S comes off, right? And now what?
Yeah, A and B.
Okay, we put A and B on the stack. The behavior will be different depending on how you order, how you're putting things on the stack, right? So in the quizzes and the homeworks, we're going to tell you to add things into your data structure in alphabetical order. For instance, it'll be specified. But let's say alphabetical order in this case. So we're going to add A and B, right? Okay, what happens now?
Pop A.
So let's say we pushed them on from the right.
We pop B.
We pop B, right. Okay, so we pop B, here's our stack, right? So what happens now?
C, D, G.
C, D, and G, right? And then
Pop G.
pop G, and what do we do then?
We accept.
So we should be checking all of these to be the goal state when we pop them off the stack, right? But let's pretend that we did that the whole time. We pop G off, we have the goal. Okay, so what is the path that we took to get there?
S, B, G.
S, B to G. And this actually highlights a really important issue that I did poorly here. So we need to be keeping track of the path, not just the end node of the path, right? So we had to reconstruct that here, that's a bummer. But what's the cost of this path? 6, is that optimal? No, it's not. Okay. Well, let's change then to breadth first search. What data structure are we going to use to keep track of our frontier for breadth first search? Q. Okay. All right. So what do we start with? S. Okay. Then what happens? We DQS and check whether it was right. It's not. Okay. So now what happens? Okay. So we add on S to A. This is what we should be doing, right? And S to B. Right? So it's a Q. So what do we do now? We DQ S to A. Right. Okay. So we DQ that and then check what?
Is that the goal state?
I'm going to do it like this. Is it the goal state?
No.
No. Okay. So now our Q looks like this. Right? We're just moving down in steps here. Okay, so what do we do now?
NQ S to A's children.
S to A's children, which is?
S to A's children.
Okay. Now what do we do?
DQ S to B.
DQ S to B, right? And so now our Q looks like this. Right?
NQ.
NQ S to C S to B.
S to B to C, S to B
To D.
to D, then S to B to G, right? Okay, and now what do we do?
We find our goal. We DQ and find its solution.
We DQ this, we check it is a goal state, and so we're done, right? And so that's S to A to G. What's the cost of that? 6. Is that optimal?
No.
No. But I thought breadth for search was optimal in some senses, right? What's the difference? Right. So yeah, so that's the closest we can get to the goal if we only count transitions from state to state, right? But not if we have costs on our edges. Okay. Let's do uniform cost search on this. Sound good? Okay, so what's our data structure look like here? Okay, with what is the key?
The key is the cost
Of
the total, like the backer stuff.
okay, good. All right, so what do we do first?
NQS
We NQS with a cost of
0.
0. Okay. So now what do we do?
DQS.
DQS, right? And add S to A.
With a cost of 3.
We'll do S to A first, and what's its cost? 3. Right? And S to B, right? With a cost of 2. Okay. let's DQ what?
Minimal cost.
Which is
S to B.
S to B. Okay. And now, what do? We still have S to A with a cost of 3.
NQ S to B to D.
To D.
Yeah.
Let's do C first. We'll just add them in alphabetical order, but
Okay.
it doesn't matter in this case, right? But S to B is C with a cost of
4.
and S to B to D with a cost of
3.
and S to D
To G.
to G with a cost
6.
of 6.
6.
Okay. Now what do?
It could be either A or D.
Could be, right? So this will depend on your implementation if you have some notion of tiebreakers or if you're letting the data structure pick for you, however it does it. Let's say that we're going to break ties, in this case, in alphabetical order, again, looking at maybe the last node, just so we're consistent, right? So we'll pop S to A. Sound good? Okay, so now what?
S to A.
Well, let's,
or-
sorry, let me maintain the priority queue the way it is. All right, what do we have?
We NQ S to A to G.
With a cost of,
6.
okay,
And
now what?
lowest cost is D.
This one here?
Yep.
Okay, so we're going to do this S to B to C with a cost of 4, right? S to B to G with a cost of 6, right? S to A to G with a cost of 6. And we're adding what?
S to B to D to G with a cost of 8.
Cost of 8. It's a lot of work. It's turning into, right? Okay. Now what do? Can you all see this up here? Okay.
What is that? It's S to
Which one are we gonna DQ this one?
Yeah.
Okay. So now our priority queue looks like 6, 6, 8, and what do we add?
S to B to C to G with a cost of 5.
Right? And now what do we do?
DQ.
DQ this one?
And it's the solution.
It's the goal. We found it. S to B to C to G with a cost of 5, and that is optimal.
In terms of length, yeah.
Okay. Well, in terms of edges, cost, the true cost on the edges, right? Yes, you first.
You say that you came across a route from start to finish that you already tried other paths, and let's say that the start to finish you found was optimal. Would you want to prune the other routes that you're taking that already hit that value but hadn't reached the goal yet? Does that make sense?
So if you reach some node in a way that is of less cost than reaching that same graph node, this is a graph node, not the tree node, right?
Yeah.
You reach a graph node in a way that has less cost than other ways you have to reach that node on the stack or in the priority queue with greater cost.
Yeah.
Would you want to prune those away?
Yeah.
Yes, I believe so. So that's, I think, the crux to answering this question of how do you do graph search well without, when out of the context of ASAR's specific guarantees on heuristic. Again, I want to double check the specifics of that and talk about it on Tuesday. But yes, I believe that's the case. Okay. Any other question?
I was just gonna say, the stop condition you stopped by taking off that state, is that because if you have a path to the end state that's the first thing in the priority queue, it must then be the lowest way to get there? Because if there was a shorter wait path, it would have to be before a path to the goal state in the priority queue.
If there was a better way way to the goal, we would have popped it off prior to popping this one off by the properties of A star. Or of UCS in this case. Yeah. That's because nothing can be called a path to the goal until it gets popped off of the priority queue, right? And we are always popping off the lowest cost thing on the priority queue, right? So, similar to how we proved this with A star, if we had both of them on the queue at the same time, which is the only option in this case, since the cost value is increasing monotonically, then we would have popped it off first, right? Okay. All right, so that's UCS, but it felt like it took a while to do, right? I mean, it probably felt a while for you to listen to. It certainly felt a while for me to draw. Did we visit every node in every possible manner over the course of that search? No. What did we not? What path did we not explore? So we had start BD goal on the queue. So we've at least conceptually considered that from a computation perspective. What did we? Is there anything else? Yes.
I guess so would you consider visiting that as like the popping or the dequeuing of it, or?
So my point is here is on the subject of the computational complexity of this. So how long did it take to run, right? And so we certainly considered every path in that we enumerated every path, even though we didn't check every path for goal states, right? But every path had to be constructed in code at some point during this process, or by chalk in this case, right? Yes?
They're also like all kind of very close. Like if you had a bunch of other branches off of the rest, then it wouldn't have gone to those two.
Sure. Yeah, so that's true. So I guess
like, this is the most it's ever going to go if you start adding more to the tree. I think. Well, that's like
depends on the tree. It depends on the graph specifically. So that's kind of the point, right? Is that UCS returns the optimal solution, but it doesn't really give us good performance from a time it took to do so perspective, right? In this case, we enumerated everything, right? Okay, so what would be the next thing we could consider? Yeah, let's do greedy first. All right, so greedy. What data structure are we going to use for this?
The one with the shortest path.
What data structure are we going to keep those in? Priority. Yep. With what as our key value? The heuristic at the terminal node of the path, right? So an estimate of the forward cost. All right, so let's do it. So what do we start with? With a key value of 4. And what do we do then? And we check if it's a goal. It's not. So now what? S to A with a value of 2. And S to B with a value of 3. Okay. And now what?
Lowest cost.
Which is S to A, right?
Yes.
And then we have S to B with 3. And what do we do with this? S to A to G with a value of 0. Okay, and now what do we do? And we did it, right? We're done, right? What's the cost? 6. Optimal? No, but that was more fun to do than the other one for me, from a hand gets tired perspective, right? So it's not optimal, but it sure got us a path really, really quickly, right? Yes?
So just a quick question, why do we do the path values on top and then for the greedy we did the heuristic values for the queue?
So because we were using, that's the difference between these two algorithms. from uniform
Oh
cost
yeah, I
search.
guess they both. Okay, because they both compare. I gotcha.
Yeah, they're both using a priority queue as the key value. That's the difference. And in uniform cost search, that key value is the backward cost, or the cost it took you to get to the terminal node of the path you're considering, right? And in greedy, it's just the estimate of the forward cost. Okay, so now we should probably do A star, right? Okay. So we're gonna use a priority queue again, I'm assuming. With what as our key value? F of our state, we'll call that X, which is equal to, let's start with G because that's what we did in the slides, plus H of X, right? Where G of X is our
Actual
backwards cost and H of X is our heuristic. Okay, cool. All right, so how do we start this? With an F value of
4 plus 0.
Good. All right. Let's do 0 plus 4. Yeah. Okay, so now we pop this, right? And we add its children, which are S to A, the value of 3 plus 2, and S to B with a value of 2 plus 3. Okay, so using the same convention as last time, what do we pop off?
S to A.
S to A, and that gets us, we have S to B, 2 plus 3, what do we add on? S to A to G, with the value of 6 plus 0. Okay, is that our entire queue at this point? Yes, okay. So what do we pop off? Okay, and that leaves us with S to A, G, 6 plus 0, and what do we add on? S to B to C with a value of 4 plus 1, S to B to D with a value of 3 plus 1, S to B to G with a value of
6 plus 0.
6 plus 0. Is that it? Okay, and then what do we pop off?
S to A to B.
That was a lot of different things. So what do we pop off?
S to B to D.
S to B to D, right? Okay. So now we have S to A to G, 6 plus 0. S to B to C, 4 plus 1. S to B to G, 6 plus 0. And what do we add? G to what? G to the value of
8 plus 0.
Okay. Now what do we do?
S to B to C.
S, B, C, right? And we're going to add its children to this queue, right, which is S, B, C, G only, right? With a value of
5 plus 0.
5 plus 0. These ones come down here. And what do we do now? Pop this and declare success, right? And it has a value of 5, which is optimal, but took a while again. So because of the specific construction of this graph, the specific heuristic values, the specific edge weights, and more importantly, the way we broke ties when we were popping things off the priority queue, A star performed in the worst case possible, which is exactly as UCS performed almost, in that it visited every path possible. Right? Yes.
Is there a utility in computing the heuristic for the start state?
I include that there for a notion of consistency, not how we defined consistency earlier. I just not really, unless you're not positive your start state isn't your goal state. And even then, actually, you probably don't need a heuristic. So, no. Maybe if there's multiple start states. which is a reasonable problem to have in some set of, you can choose from a set of star states, maybe. But no, not really, I just put it up there because I want to be consistent where every node has a heuristic value. Okay. Do we all feel good on tree search with these algorithms? I don't think I ever fully went through the entire search of every one of these. I wanted to make sure we did it together once at least. Okay, so let's move on then. Let's talk about graph search very briefly. So I'm not going to do every algorithm again with graph search. And in fact, I was looking at it before class, and I think none of those would have actually changed if we were doing graph search instead of tree search, coincidentally. But let's talk about graph search. And we're just going to do we'll just do DFS. Okay, that sound good? Okay, so let's start. We have S, right?
We're using a stack, right?
We're using a stack for our data structure that's storing the frontier. And we also have to keep around our closed set, right? So here's our stack. Okay, so we have S, we pop S, that gives us S to B, right? We add S to our closed set, right? We pop S to B, that gives us S to B to C, right? We add B to the closed set, yes. Okay, then we pop, for demonstration's sake, let's not use the closed set for this instance, just to see what happens. If we're doing tree search in this graph, then we'll talk about this, okay? So let's just pretend I use this. S to B to C, okay. So it's the only thing, so we pop it off, and what happens? S to B to A, and S to B to C. Sorry, this should have been C to A, right? And this is S to B to C to B, right? I mean, I think you're going to see where this is going pretty quickly, but it's a stack, so we take this one off, right? And so now we have S to B to C to A, and we add this one's children, which is S to B to C to B to C, right? And then we're going to pop this one off, so now we have S to B to C to A, S to B to C to B. You want me to keep going? To C to A, right? And also S to B to C to B to C to B. Am I doing this right? Is that right?
That's right.
Okay, that's enough BCBs. Okay, so what do we do now? No, we're going to stop. Okay, let's revisit this with our closed set. But you can see what's going on there, right? And it wouldn't have gone that way if we had gone in reverse alphabetical order and how we were adding things, but you can't always know that in advance, so it's not like you can use that to kind of prevent this behavior, right? Anyway, that's why graph search can be important, especially in DFS, but also because of the repeated subtree structures that we saw in the other example on the slides, it's also important in the other ones, even though they wouldn't get stuck in a loop like this, right? Makes sense? Okay, so let's just do this example real quick with our closed set. S, we pop S, add it here, S to B, right? We pop that, we add B here, S to B to C, we pop that, add C here, S to B to C to A, S to B to C to B, right? Because nothing has been on the closed set yet, right? That we popped off, which is when we check. So we pop this one off, right? this has B as its terminal node. We already have that. We don't expand on this, right? We ignore it forever. Pop this one instead, right? Add A to our closed set. S to B to C to A to G. It's the only one on stack. We pop this, we declare victory. We all go home, right? Yes?
Quality of life, can we just check before we add stuff to the stack? Like, oh, I'm pointing at this node with this edge. I've visited that node before, let's not put that on the stack.
In this case, where you're not considering edge costs, that may...
No, not cost, just like you put
I know what you mean. You check before you put it on the stack. In the case where you are considering edge costs, it may matter. I'll look into it, but for similar reasons as to why we don't declare victory when we NQ a goal in A star, there's probably an analog here. I'll look into it. It's a good question. Sound good?
Yeah.
Okay. Very good question. All right, so do we feel like we've kind of demonstrated the search algorithm sufficiently for now? Okay, so why don't we take 5 minutes, and then I want to talk about abstracting some of these search problems into interesting places like navigation to the self-driving cars.
So I received a message you got. So you're doing a check with the case machine, right? Running it on Python.
Oh yeah.
And so I can do that when I get back to my computer because I got permission over there. But do we still know any reasons why it's not working specifically?
I mean, I think it works on Windows. Someone came to the case session and worked fine on Windows.
So if I
is it PyCharm specifically?
Maybe because I did it with a version of it without it. I can send you the 3 files I wrote. Maybe
Did you modify the files before you ran them?
no. So
how did you install Python?
So I went on the website, downloaded the latest version of Python, ran its installer, restarted my computer, had Python on my iPad. Just like
so how does PyCharm look at Python?
So PyCharm, I had to go into PyCharm, I had to give it an extension, so I had to actually manually find the Python.txt, send it over to PyCharm, and run it.
Have you just ran it on the command prompt?
So yes, I did. Like if you open up like a normal Python file on Windows, you just right click it and edit it, which isn't PyCharm related.
Yeah, it's just the text.
Exactly. And so you can run the module that way as well, and that gave me the exact same.
What about just invoking it from the command?
So
Python autograph.py.
So I don't understand that. Like you mean go on the console, locate the file, Python autograph. It doesn't print anything.
Oh, it doesn't print anything?
Yeah.
I was running into that problem with another student.
Yeah.
It doesn't print anything.
Like it literally prints nothing. It'll accept the command line, but then move on to a new line.
Yeah. So what we had to do was open up. She used an Anaconda.
But I had the same. One person I had today had that same thing where you have normal Python from the command line and Anaconda.
Yeah, but Anaconda. So maybe you should try using the Anaconda software and then opening an Anaconda terminal.
Okay.
Yeah, because the tutorial shows how to do it with Anaconda.
Yeah.
Did you look at the tutorial?
Yeah, I don't know, it felt kind of redundant because I'm already working on Python 3 in PyCharm, so it's should work the same in a project with it.
Yeah.
It's kind of frustrating that
Yeah,
I have to go through all these things to do Python.
I mean, I don't know. I would need to literally just sit down and look at it and debug it and code and stuff, right? I don't. Everyone's machine is different.
Exactly. I mean, that's
so,
why
I'm sorry, but I can't do that much.
No, I know that on that end. The shitty part for me is I don't own a laptop, so like I get that.
Oh, you don't own a laptop?
Yeah, I literally don't. So I
have like a desktop.
Yeah, I do everything on my desktop.
Okay.
So like, if I could, I would literally put my laptop there and try to read it.
Gotcha. Sorry.
Yeah. So it's kind of like the harder thing to like go and like try and debug and all that stuff.
Well, it sounds like either try the Anaconda or if Python is still like, it sounds like that could be like a Python specific configuration thing.
I would have thought so, but running an idle shouldn't be any different, or it should be different than this.
But I just think the Windows command prompt maybe like suppresses the output from Python. So to get an output from the program, you need to feed it to like standard output, right?
Well,
so
actually,
I don't know what the Windows
idle does pretty good. When I do it on idle versus not command line, but I do it on idle. When you install it on Windows, there's like a little idle that like installed into it, and there's a client Python module. So well, it prints all the same errors that Python prints.
Okay.
But again, like if I run like the individual files, like if I run like the addition.py, if I run the shopsmart, like all those work because I print out tests and I actually like did assertions on those.
Yeah.
So those run everything, all the errors that I read come from the auto.
Did you just Google those like specific errors?
They were, but they were things I was very unfamiliar with. Like you guys are reading like I don't know how you're reading the sets on the auto-graded. I'm not sure how they work.
Yeah, I don't know.
Yeah. So like it was kind of like it got to a point where I was literally trying to debug the autograder, and then I was like, why am I debugging the autograder? I'm supposed to do these things. So I was hoping that there might have been like a simpler situation. But if you're saying to do it on Anaconda, I mean I can have tried it. Yeah, it's like
Maybe try that. Just start from the Anaconda. I got yeah, sorry. There might just be some weird configuration and it doesn't play well with that. Maybe that's why he had people download Anaconda. There's some environment, right?
Yeah,
because Anaconda has a custom set of environmental variables, so maybe there's some configuration that he's reading.
I'll do that today. I'll literally run it. I'll get on Anaconda and I'll run it on if I still don't get it. I'll do that.
Sounds good. Yeah, sorry, it's so frustrating. And the whole frustration of it is like, this time it's easy.
This time
but like, the DevOps and just like getting your computer set up, that's always going to be the
So I'm not like super like pissed off about it either, because I know that this class has literally never had Python before, so I'm expecting this type of crap, but like I'm a little bit that I'm like one of two people here that's actually trying to.
I would say try to follow this program. What is
That's what I'll do.
Okay, let's get started again. All right, so we're going to start in kind of a simplistic model way, and we're going to add complexity a little bit as we go on today. But by the end of this, hopefully, if we have time, we're going to be talking about search-based concepts for self-driving cars that were actually applied on self-driving cars. Okay, so we'll start simplified. We'll add complexity as we go, and we'll end up someplace relevant. Does that sound good? Okay, so let's consider a car. It's got four wheels, right? It's got a front, maybe, and a back. It goes forward, it may go backwards, but let's pretend it doesn't for a minute. Okay, this car goes forward, right? And the car can also turn, right? Okay, so let's say that we want to go, this is going to look very similar to our Roomba example from before, where we have this discretized model of the world. Let's make it a little more interesting. And our car is sitting here, facing this way with its little wheels. And we want to get to this square here with any orientation of the car. Okay? but there's like some stuff in the way. Right? Okay, so in the Roomba example we did last time or 2 times ago, whenever it was, we said the Roomba can kind of move to any adjacent square. Maybe it can move diagonally, maybe not. Who really cares? It all looks kind of like the same problem at the end of the day, right? Just depending on your action space. Right? So let's talk about the similar analog here, where the car, instead of being able to move sideways, which is generally not how cars work, right, can move forward and it can turn left or right as it moves. Right? So let's say our car has, this is a simplifying assumption, 3 actions. It can go forward 1 square, it can turn right, and it can turn left in a 1 square way, right? So in this case, it ends up in this square in the same orientation. In this case, it's going to end up in this square, but it's going to be going in this direction, right? And in this case, it ends up in this square, but it's going to be going that direction, right? Okay, so that means this car here can end up here, can end up here, or can end up here, right? And if we were here, we could end up here. Might be a bad idea. We could end up here. Might be a similarly bad idea. Or we could end up here. Maybe a reasonable idea, right? Okay, so that's our model, right? And we want to get to the goal. So if we talk about this in the context of the search problem, what does our state space look like? What's its dimensionality?
Combination of all squares and possible orientations.
Right, which has dimensionality.
3 times the width times the height.
So not its cardinality, but its dimensionality. It's 3.
Yeah.
Right, we need to care about its position, which can be parameterized by 2 values, x and y, and its orientation, which can be parameterized by a 3rd value, right? 3-dimensional. So now it's a little different already than the Roomba problem, right, where we only have the 2. But that's not going to stop us. So what's its action space look like? It's got 3 potential actions, right? We just wrote them out here, right? And so do we know the successor function then? Can we say for any state, which looks like 3 of these grids stacked on top of each other, right? For any state, do we know what the successor state would be if we applied any of the 3 actions it's got? We do, right? We have a start state. We have a goal state, right? So does everybody understand why this is 3-dimensional, the state space? So I guess you can imagine the car sitting here, right, in that direction. And you stack on top of that an identical version of the grid, right, but the car's in that direction. You see what I mean? Does that make sense? Right? Okay, that's good. All right. So we've got a start state, we've got a goal state, we have our state space defined, we have our action set with a transition function, or successor function defined. So could we search on this with the search algorithms that we've talked about?
Yes.
You could, right? In fact, it's a pretty small problem, so you could run any of your searches, being careful about DFS, and end up with a solution, right? Well, let's get a little more complicated. Maybe let's say there's a cost. What should a good cost be? It's not that much more complicated. It's more packed cost than anything.
Movement or movements less turning.
So it's cheaper to go straight than it is to turn?
Sure.
That could be reasonable. We'll get to something like that in a minute, but let's just say that your cost is just a transition. It costs as much to get to this square as it does to this square. Maybe it's a bad assumption, but we'll just say it's the assumption for now. Okay, what would a good heuristic be? The Manhattan distance from your current state to the goal. What does the goal set look like? It's not one state, is it?
It's 3 1 3 or 4
It's 4, yeah. Yeah, there should be another one of these, right? The goal is kind of a column here, right? Roughly in this abstraction. Yeah, so it's this state with any orientation. Okay, so does that change our heuristic function? Do we have to consider that?
Yes.
Do we?
We wouldn't have to we would have to consider positions, which might be a heuristic.
So,
When Manhattan distance is ever zero, you're at the goal.
Yeah.
that's true. Is it,
I don't think that heuristic really changes based on the orientation of the car.
so, let's say, so there is a Manhattan distance of 4 to turn the car all the way around, right? You see what I mean?
Does the equation,
Yes.
does the equation for Manhattan distance include orientation? I thought it was only sort of the.
Well, it depends on how we define it. Is the Manhattan distance being defined in this 3-dimensional grid? Right, because this is really a stacking of grids. Right, and there is a Manhattan distance in 3D. Right. Yes?
Would we include that orientation when we said the only ways we can move is to go forward, left, and right? Like,
Yeah, so that's a good point.
rotating.
You can't stay in
place
space and rotate.
is not possible.
But it's a heuristic, right? So maybe we're adding actions that we don't have in our model. We can't move in Manhattan distance from all states anyway. Right. Anyway, you have to think about these kinds of things. I believe that you would want to ignore the orientation dimension. That'll for sure get you an admissible Manhattan distance, or an admissible heuristic in Manhattan distance. So you just do a Manhattan distance on the 2D grid rather than on the 3D one, but anyway. Okay. So we could do A star on this, right? And it would work really, really well. And it would go around obstacles. It would find you the optimal solution.
Be a lot of turns.
Would there be?
Yeah, because you go further by turning. Because going diagonally is faster than.
But not in our cost metric, right?
But that's what I'm saying, right? Is like it costs less to go further. It's like the Euclidean distance between a diagonal spot is
Oh, yeah, that's a good
larger
point.
than it is.
Yeah, that's a good point.
horizontal.
So it might highlight why this might be a bad abstraction for how cars work, right? Because this isn't how cars work. At least the cost doesn't really equate. Yes.
So when you turn, is it not taking 2 squares to turn?
Well, we've called it 1.
Okay.
We kind of get to define that. Like in one way you could go about doing this, like in the real world, if you assume your environment model is sufficiently detailed and you know enough about it, is you're defining some set. This is kind of waxing poetic about how robotics works, apparently. But you're defining some set of potential actions. At the end of the day, you're going to need one more layer, which is some controller on the car to actually follow those actions. But if you define some atomic set of actions, then you chain these things together as long as you can execute that chain with the actual vehicle at the end of the day. It works. Under some assumption. Anyway, all right, so let's talk about making this a little more realistic then. What property do cars have that we haven't really talked about here? All right, sure. So we could conceptualize a similar version. Where we back up? That wasn't really where I was going though. What might change how far we go in one step?
A hill.
Stop signs. Velocity is what I'm going for.
So a hill.
A hill, maybe. Yes.
Being able to go diagonal without changing orientation.
Being able to go diagonal without changing orientation would be awesome, but may not be possible. But you can imagine some atomic action that looked like that, right? As long as you can do it, it would work. So you could define this problem that way. Then research might be a little easier, but your resulting trajectories might be a little strange looking. Yes?
Perhaps you're only able to see what's in front of you.
You're only able to see what's in front of you? That's a great point. So what would that look like here? Maybe you have some like ball around you that your sensor can look into, right? You don't have any other map. So we talked at the very first day about this notion of replanning, where you would plan for what you see, execute what you see, update your information of the world based on what you saw on the way, and continue, right? You can imagine building up a model of what the whole environment looks like as you go. You may have to back up, right, because you find yourself painted into a corner potentially. But yeah, yes?
So how would we know Manhattan distance to a goal state if we only have like a sensor view on this car?
Right, so when we talk about Manhattan distance to the goal, that is one thing that we would know without knowing about obstacles in the environment, right? let's say your goal is defined by some GPS value and your current state's defined by some GPS value. You can get Manhattan distance out of that without any sensor, right? Other than a GPS sensor, right? So let's think about velocity, right? This kind of model assumes that we're going slow enough that it doesn't matter, but maybe that's not what we want, right? So let's say that our car now, if it's moving fast enough, can go farther in the forward direction, you can go farther as it turns in one step, right? Do we need to consider a different kind of state space? Right, if our action set depends on the velocity, or our successor function depends on the velocity, then in order to apply either of those, we would need to know the velocity of the car, right? So we could add the velocity of the car to our state space, right? That probably means that we're going to want to add some actions to our action space, right? So you could imagine just having a set of velocities from which you can choose, right? You can be stopped, you can be going backwards, you can be going forwards with value 1 or value 2 or value 3, you know, in some unitless world, right? And our turning radius may depend on velocity, right? Because some turns aren't really safe if you're going too fast, right? Maybe you would roll the car instead of turning. That's a bummer. But is instantaneously setting the velocity really a good way to think about cars? Is that how you set the velocity on your car? You don't, right? Yes?
Maybe you have to have an action to slow down or speed up, or maybe choosing a specific action could slow you down or speed you up.
Right, so maybe you have some way to apply a delta to your velocity, but not set it from some set of values, right? Those look kind of conceptually similar abstractly, but they're kind of different, right? So then what would your action space look like if you look like acceleration rather than velocity, right? And that's how we operate cars generally.
It becomes like a continuous action state if it's a delta.
So that's another very, very good point, is that in the real world, cars don't live on grids, right? Our set of potential velocities don't live in a discretized notion, right? We can't apply discretized accelerations to those. So it's all continuous space, right? But if you have, like I said, a controller that allows you to pretend that the world does live in that way, and it's robust enough to do so safely, then you can consider real world problems in a discretized way.
Could that be like a possible heuristic? Like going straight would cost less than having to make a turn?
Potentially, yeah. Okay, so maybe what you would want is a state space that has velocity, right? And your action space includes acceleration, which is just applying deltas to that velocity, right, from some set. Maybe in the real world, your state space should also consider something about your current setting of your turning radius, right? That's how our cars work, right? You're set at some turning radius, and you can apply a change to that, but you can't set it instantaneously to a different value, right? Yes?
The composition of our like options of turning or going forward with always slowing down or speeding up in this step.
Right, so exactly. So it becomes much harder to look at what the grid looks like what your discrete set of states that you can visit looks like. It's still a discrete state of set of states, though. But yeah, these get a lot more complicated, right? There's also little ones. And some of these are accessible at different times that others are not, depending on your current velocity, et cetera, right? But at the end of the day, just because you can't draw it on the chalkboard doesn't mean you can't search over it, right? So in the way that we've defined it with accelerations on turning, accelerations on your velocity, and the world state, and a state for your current velocity and your current turning, you could do literally graph search and navigate a car in exactly the same way. It's just your dimensionality is going to be much higher, so that good heuristic is really going to matter a lot more. So these are like the building blocks on which at least one of the DARPA Grand Challenge first self-driving cars navigated with. Anyway, living in a continuous space, I believe they discretized it, but had a controller that would allow them to do so robustly. If you consider these in a continuous space, this looks very, very similar to some of my research in medicine, which is steering needles through bodies around sensitive anatomy. But it's a continuous space. Its state space is 5-dimensional, and your action space is 3. So, if anyone's interested in that, I'd love to talk more about it, but I will not bore all of you with it. So, let's call it there. Alright, thank you.
I also want to check if I could say